previous sessions, we were looking at the convolution. First, we considered the concept of convolution in one dimension, and then we extended the same concept to two dimensions. We applied the concept we learned to program or to code the convolution concepts in MATLAB, right? And now let us try to continue our discussion on the convolutional neural networks. So as a first part of the convolutional neural network, we looked at what is convolution, right? Okay, now let's quickly go back and try to recall what we discussed when it comes to the convolutional neural network. Okay, so basically we understood that right, there is a short form CNN, stand for convolutional neural network, right, which in general is also referred to as the ConvNet. Okay, so it's a type of a deep neural network architecture. Just hold on for 1 second. So we considered convolutional neural network as the fundamental architecture of the deep neural network, which has many number of hidden layers that compared to that of the simple artificial neural network, right? So what was the fundamental difference? The difference of deep neural network and convolutional neural network is that it has a large number of hidden layers, and even the internal architecture is slightly different in terms of the activation function, right, etc. So that's what we considered first, right? And we actually mentioned that the basic application of the convolutional neural network was to classify images. Later on, it had been extended further for many other applications as well. Okay, now when it comes to the machine learning, right, there is one step which is called as a feature extraction. So even in the neural network, you can see this diagram, which is very clear that it's the representation of machine learning based techniques. ANN simple neural network falls under this case, and you can see that there is there is a specific layer called feature extractor. So the feature extractor comes into picture because the neural network expects inputs, right? They are representing the features of uh, the data set which we want to classify. The training data will have input and the correct output, two parts, right? And those two parts uh, cannot be directly given to the classifier because the data set is huge, right? So you have to extract the specific features and give it to the machine. So there is a block called feature extractor followed by a classifier. Classifier is the normal machine learning based classifier, or it can be even our ANN. Okay, but what happens when it comes to the convolutional network is that it's a very specific, very special featured one, because the convolutional neural network is a single block which can perform the feature extraction as well as the classification, right? So maybe the question is, what's the big deal in this, right? You clubbed two things and you made it a single block. Maybe that could be the question. So the answer is that no, it's not just that thing. See, when I say feature extraction is automatic, right? The convolutional neural network performs that job automatically. This also indicates that you don't have to specify what feature you want to extract, because there are many features, right? Related to a data, there could be n number of features. You don't have to specify which feature you want to extract. Okay, so that's the big deal, right? You don't have to say, okay, find the biggest number, find the smallest number, find the mean, find the variance, find the covariance. No, right? Depending upon the data set, the convolutional neural network extracts the features by itself. First thing, okay? Then going ahead. So once the features are automatically extracted, it will use its own classifier to do that. So we have two sub units of the convolutional network. that has first part will do the feature extraction part, second part will perform the classification part. So the general architecture, you can see that the feature extraction network will be a convolutional layer followed by a pooling layer, again convolution, pooling, etc. This will repeat as many number of times as we want. And finally, we have a classifier network. That's a normal neural network which will perform the neural network operation. So, right. So this was the first idea, right, which we had considered, followed by we also looked at the convolution right after that. So, right now, since we finished the convolution, we'll directly continue our discussion. So, we'll continue the discussion related to the convolutional layer. Okay, so this is the convolutional layer. Now, uh, so previously we have seen that, right? Uh, in the convolutional layer, which this is the important part, right? Which is one side of the feature extraction neural network, right? And we have a pooling layer on the other side of this, right? So convolutional layer is nothing but, so this layer is basically, this is, this layer is the one side, the first side of our feature extraction network. Okay, then followed by this, on the other side, what you have another layer that is called as a pooling layer, right? So I'll write that as well. So on the other side, we have the pooling. Pooling. Right. So we'll see the pooling layer later. Let's look at the convolution layer first. So as we know, what is the work of this particular layer? The convolutional layer basically generates some new images from the given image. The new images are called as the feature maps. All right. So the convolution layer generates new images. So why you call it as image? Because image is nothing but a matrix representation, correct? So we perform convolution of that input image or input matrix with another matrix, and the resulting answer is also a matrix. So you call it as an image. All right. So generates new images, and we have a name for that. So called the feature map. All right, it's called as the feature maps. So the feature map basically, it contains unique features of the original image, right? So what is a feature map? Feature maps are basically, you are trying to accumulate, I can write accumulation, accumulation of some of the unique features. All right, unique features of the original image, right? You get, let's assume that we, our intention is to classify uh, the two categories of images which we have in our database. Maybe one class is a cat, another one should be dog, right? So what are the unique features of the first class of image, say cats, right? So it will be extracted. That's what is a feature map corresponding to that. And you have another feature map corresponding to a different one, right? So the second class dogs also will be the same, right? So unique features are there. Now, the operation of the convolutional layer is very different compared to the other neural network layers in general, right? So we already have seen how the neural network works, right? Any layer, right? How it works, we know that, right? It actually calculates the output of a layer, right? From that output of the layer, you calculate the error, right? From the error, calculate a gradient, use that gradient to, right, calculate the change in the weight and update your weight, right? This is how it works, right? Any general neural network works in that way. That's what is a training part. But here it's not a training part, right? Because their working is completely different. The operation of a CNN is completely different compared to the other neural network layers. So this layer does not employ any connection weights or a weighted sum, right? That's what, because you already saw that what is a convolution in 2 dimension, right? In 2 dimension, it's simple convolution operation. So let me write that sentence over here, right? So this layer operates in a very different way compared to in a very different way compared to other artificial neural network layers. They're different. How? Because because this layer, that means we are talking about the convolutional layer, does not employ it will never employ connection weights. If you have a weight with respect to a connection, then you need to multiply. It's not convolution, correct? So that's why it's slightly different. It does not employ the connection weights, and right, there is no question of weighted sum, okay? And a weighted sum, that concept is not there. Instead of that, what you are going to have inside that, you are going to have some filters, right, called convolutional filters. They are small matrices, right? So the numbers you enter in the matrix, in those matrices, depend upon what type of features you want to extract. Okay, so we'll talk about that later, but let me write the point here. Right. So instead of having the weighted sum or the connection weights, right, this layer consists of filters. Okay. So instead, this layer contains filters called as the convolution filters. Why do you use it? To convert the images into the feature maps. Convert the input images into the feature maps. Maps by performing the 2D convolution. So the image filters will be used to perform a convolution between input image and that. Okay, so when you do that, you get what is called as the feature map as an output. So that's the fundamental idea over here, how the 2D convolution can be used, right, to get the convolution results. The result of this 2D convolution itself is called as the feature map. Okay, now let's look at the process, how this is going to be done, right? I'll show you a one image quickly that uh, gives you an idea what are the different features that we are trying to extract from an input image. It's not that you take only one set of features, you can get multiple features resulting in multiple feature maps. Okay, so that's our idea. So let me just paste one image. So as you can see here, so we have an input image, which is the image of a dog, right? So it is getting convolved. You can see the convolution operation over here. This is what is an indication that we are performing the convolution operation, right? You can see that these are the convolution symbols, right? So input image is getting convolved with the multiple types of filters. Where are the filters? You see this, these are the filters. You can see the size of these filters are something like 5 cross 5, right? Like we took an example where we had a larger matrix getting convolved with a smaller matrix. Okay, you perform the convolution, right? And maybe you can have some thresholding operation or some operation represented by a phi over here. We'll talk about that later. So that at the end, once you finish this operation, right, you get, right, something like the four images which you can see here. 1, 2, 3, 4. You can see that this is a blurred image, right? Like maybe that particular filter will perform the blurring operation or low pass. It's called as a low pass filter. It will pass only, right, the lower frequency components. Okay, maybe some images are simply you would remove the colors, right? You can see that the color has been removed to get a black and white, or right, the negative of the image is kept over here, right, as a feature like that. So you can see that, right, depending upon what type of filter you use in this convolutional layer, as a result of that convolution you get the features accordingly, right? So we have to develop the filters according to our requirement, right? So simply put a matrix over there representing the feature you want to extract and perform the convolution with the input image so that you get the overall feature maps as required. So this thing itself is very clear that what you are trying to do. Okay, now, so I think the idea is very clear. Let me write a point over here related to this. So here, the process of convolution inside the convolutional layer, right, is denoted by the star operator. Okay, so in this, in the diagram here, the star operator indicates or it represents the convolution operation. Okay, and we have a phi over there, right? So denotes some sort of activation function. Okay, that decides, and activation function. So you can see that there are several grayscale icons between the operators. They indicate the convolutional filters, right? So what are the characteristics of the convolutional filters used over here? Right, they are smaller in size compared to the size of the image. You can see that the image is large in size and these filters are smaller in size. And again, the filters have some values. They denote uh, the grayscale, right? Convolutional layer generates the same number of feature maps as that of the convolution layers. So 2 points are important. Okay, let me write both the points now. The square grayscale icons are the convolutional filters. Are the convolution filters. So convolutional layer generates same number of features or feature maps as the convolution filters. How many number of convolution filters you use? Same number of feature maps are going to be generated. Okay, so the convolution layer generates the same number of feature maps as, so as many number of filters. Okay, so as the filters. So in the previous image you can see that there were, we used 4 convolutional filters, so you got 4 feature maps. Okay, moving further. Now let us try to explore some of the details of the convolutional filter. Okay, so what are the characteristics that we can observe from this given diagram? The first thing is that the filters used in this convolution layers are fundamentally a matrix. It's a matrix. Matrix means two-dimensional array, right? So that's the first feature that we observe whenever we consider a convolutional filter. Okay, so these filters of the convolution layer are 2D, two-dimensional arrays. So that's what we call as matrix. It's a matrix, right? Usually the standard sizes used even in the industry now are either 3 into 3, 5 into 5, 7 into 7, and so on. Okay, matrix. So I'll write usually 3 cross 3 or 5 cross 5, etc. in size. Right? So some of the special applications even use 1 into 1, right? That's fine, absolutely. Okay, now let us look at an example just to see the filter's value. Okay, so for an example, let me consider a matrix. So for example, you can have a filter such as 1, Okay, so 1 1 0 0 1 0 1 1 0 0 1 0 1 1 1 0 0 1 1 0 0 0 1. You can see that this is a 5 into 5 example of a filter. Okay, all right. So in the previous example also we considered the filters of 5 into 5 size. Instead of writing a value over there, we wrote the grayscale values. Okay. Now, the values of the filter matrix are fundamentally determined by the training process itself. Okay, so let me write that point over here. The values of such matrices or the filter matrix. Values of the filter matrix are determined through a training process. So this aspect is very similar to the updating process of the uh, connection weights of an ordinary neural network. So I'll write that point over, right? So similar to the weight updation process, weight updation process of our regular ANs. Right. Now, let us already we anyway we know that what is convolution. We have performed the convolution in one dimension, right? Later on we expanded that to two-dimensional case. Okay, now in terms of the image, right, let us try to understand the let us consider the image processing version of the convolution. Okay, it's again it's another example, that's all for us. Since we already have solved many problems of 1D and 2D convolution, this just becomes a practice problem for us. Okay, right. Let's quickly go with the process. That is, let me consider an image. Okay, so consider a 4 into 4 4 into 4 pixel image. All right, so this is the image, that is I is our image. This is equal to 1 1 1 3 4 6 4 8 30 0 1 5 0 2 4. Okay, so this is our image. Now this is actually a part of our part of some image. Okay, this has been collected from an image. I'll show you the actually what is happening when we do this. Okay, what's the physical meaning of convolution, what is the result, and we'll be able to do the analysis of the result in this case. Previous problems were random. Okay, whatever we solved in the examples of 2D and 1D convolution, they were at random. They were not having any specific meaning, because our intention was just to learn the process. But now we are going to look at the image processing aspect of the convolution. What happens? What exactly is going to happen when you use the specific filter to perform the convolution? Okay, so I want you to convolve the two signals. Now let me use a filter. I'll call it as F. The filter that I'm going to use now is a 2 into 2 filter, 1001. Okay, simple, 2 into 2. So the original image is 4 into 4 and the filter I'm using is 2 into 2. Alright, so now I want you to perform the convolution to get my result, right? So the result is, let us try to denote the result as, say, y is equal to, y is my output, okay? So y is equal to I image convolution with the filter. All right, so I want you to perform this circular, the two-dimensional convolution and give me an answer. Okay, please take your time and finish it. Okay, so when we perform the convolution, we get the following answer. So that is equal to, let me write 7, 5, 9, 10, 4, 4, 7, 9, right, 32, 2, 5. This is the result of a two-dimensional convolution. Right. Now, okay. So this anyway, we are very familiar with the process of convolution, right? So in this case, this is or I is the image, right? Let's look at the terminologies once again. This is the image, this is the filter, and this is called as the feature map. Now I should justify why I call this as a feature map, right? So let us try to take a very closer look at the feature map. Now I want you to concentrate on this number, that is 32. Okay, what exactly happened at this particular cell? Why the value, right, resulted in a larger number over here? Obviously I can say that it's because these two numbers are getting added, right? That's true, right? It's getting added in this process, right? Now, so when I applied the filter over here, right, this particular filter is being applied over here, and this resulted in the calculation of 30 into 1 plus 2 into 1, so you added up to get the 32. All right, that's fine. Mathematically we understood that, right? So my feature map is basically asking for the diagonal elements only, right? You see that the principal diagonal is only present in my feature, the filter. Filter says that, okay, I need only the principal diagonal elements of your original image, correct? Only they are significant for me. I'm not worried about what is present in the along the other diagonal or what are the other elements. We are not worried about. So the idea is that I can notice from this particular representation that the submatrix of the image which matches to the convolutional filter, in the sense, right, both are the diagonal matrices with the significant numbers on same cells, right? So the convolution operation results large values whenever the input matches to the filter, correct? You can see that this particular matrix, what you see here, right? So the red colored highlight region, it is exactly matching to the filter, I can say, right? other than the diagonal elements, you can see the particular matrix what you see here, right? It exactly matches, right? Whenever the two matrices match, I get the highest output. Whenever the image matches to the filter, yes, output is high. I just justified you that now. Okay, so let me write one point over here. That's what we learned from this. Previously, we never considered all these aspects because our intention was just to learn convolution. All right. So, right, I can write one point here, right? If the sub matrix from the image, that is the input, okay, from the image matches the convolution filter, right? If at all it matches to the filter, right? What is that case? In this case, only both are diagonal matrix, because I can see that my filter is a diagonal matrix, and even this sub part or the sub image or the sub matrix is also diagonal matrix. Only principal diagonal elements. Whenever it matched, I saw that I got a bigger answer. Okay, so matching is identified by results being larger compared to the other entries of your feature vector. So I can actually, by just looking at this feature map, I can say that from this result, what is your conclusion, right? There is a component of the image exactly matching to my filter at this position, right? I can even identify that. So you see, that's the beauty. Okay, right? So let me finish the sentence. If the submatrix from the image matches the convolution filter, what happens? Then the process of convolution, right? It results in, or I can write yields larger values, larger values in the feature maps. So feature map is that. So let's check another one, right? You see, when it becomes minimum, I just want to talk about that as well, right? There are some minimum values even present in my final output. Okay, so let me check that. I'll change the color. All right, so let me bring this particular matrix over here. Okay, because my matrix is just like this, and you see it is not at all matching, correct? You see, you don't have this diagonal. Actually you have the other diagonal present. So I'll actually highlight the other diagonal in my image. So my image actually has the other opposite diagonal. So what I am looking for, right, in the image through my filter is those elements which have the principal diagonals only, not the other diagonal. But in this case, you can see, right, this actually has, there are highest values, 30 and 6, bigger values present, but they are present in the opposite other diagonal, non-principal diagonal. So because of which your result is just 4, right? You see, it is minimum, there it is not at all matching, correct? So you can see the huge difference coming into picture. Whenever it is not matching, right, your result will be small, indicating that there is a wrong alignment of the elements that you are looking for, such as the principal diagonal. I'm looking for principal diagonal, but in the image I have the other diagonal opposite. That is indicated by a smaller value as a result in the feature map. Okay, very important aspects to learn. Okay, let me write that. Okay, I can write the larger number, like example 30, right, does not affect the convolution result, right? Because what's the reason, right? The input image sub matrix does not match the filter. So, and hence it resulted in just 4 as answer. So what is the conclusion? So from this, the conclusion is that if the input image submatrix does not match to the convolutional filter, you are going to get a smaller value or even zeros in the feature map. So that's the very important observation which we are going to do now. So this implies if the image sub matrix doesn't match to the convolution filter, okay, if it does not match the convolution filter, right, then the feature map results in smaller values. Okay, now in a very same manner, right, let us try to perform with another filter to check what exactly is going to happen, right? Will it result something or not? Let's check. Now I want to do the following convolution. So the image is, I'll directly write, just give me the answer when ready. So this is 1113, same image, okay? This is 4 6 4 8 30 0 1 5 0 2 2 4. Okay, just look at the filter now. I'll change the filter. I want you to convolve this with the following filter. See, I changed my filter's orientation. I'm not looking for the principal diagonal. I'm looking at something else. Please perform this convolution. So the convolutional result is as follows: 5 7 7 36 4 9 right. So 0 3 7. Now you can see that, right, since we are looking at the other diagonal which exactly matches, right, I have a other diagonal highest. That's why this resulted, this into this resulted in a 36 over here. Whereas, right, I'll change the color. This, when overlapped with this for the convolution, you can see that that's not at all matching, so I got a 0. So principal diagonals though exist, whereas I'm looking for the other diagonal happens at the right at this particular position in my feature map, right? So that's what is the conclusion. All right. So if you want to summarize, the convolutional layer operates on the convolutional filters on the input image and produces what is called as a feature map. Okay. And the features that are extracted in the convolution layer, right, determined by what you call as a trained convolutional filters. So the features that convolution layer extracts vary dependent on which convolution filters are being used, right, during the convolution process.